So I welcome you again to our department colloquium. It's good to have so many here. It is also good to have with us our distinguished speaker, Haihe, who will talk about formal construction and generation of algorithms. We look forward to hearing.
It's my pleasure to give a talk here. And I think it's a great chance for me to exchange our ideas with you. And my presentation is on formal construction and generation of algorithms. First, I will give an introduction to the background and explain how the problems arise from this area. In order to address those problems, we have developed series of research works, and some of them will be presented here. Finally, our ongoing work will be briefly introduced. So today, the software are everywhere, and more individuals and society rely on advanced software systems, from the safety critical fields to the critical fields, such as the bank, communication, manufacture, education, economy, transportation, and medical devices, and aeronautics and astronautics. We can hardly do anything without software. But the current situation of software development is not optimistic, as software often cannot be delivered on time and within budget, and the errors and omissions in the early stages are often discovered in the later stages, and the cost to go back and to make a change is highly expensive. So there are many big ongoing projects have to be cancelled due to the inadequate planning and the frequently change requests and the cost and the budget overruns. For example, in 2002, the Australia's largest water provider, the Sydney Water Corporation, had to cancel its project to automate customer information billing due to the inadequate planning and cost and budget overruns after it has invested $33.2 million. More details are given on Wikipedia website. There is a list of failed and over-budgeted software projects. Also, the software bugs are everywhere. And the professionals are always struggling to cope with these bugs. Some of the software bugs are merely annoying or inconvenient, but some of them have extremely serious consequences, either financially or as a threat to our human well-being. For example, in 2006 in China, a guy named Ting found an ATM machine was out of order due to the software bugs, and he maliciously withdrew 175,000 yuan and ran away. Finally, the guy was captured and sentenced to life imprisonment for larceny. And in 2011, there are two high-speed traveling trains collided on a viaduct near the Windsor city of China, and 40 people were killed. At least 192 people were injured. Through the later investigation, we found that the train failed to collect the data and update the data, so the driver was misled to speed up the train and lead to a crash with the wheel of another train. And the following is a list of some notable software bugs with significant consequences. In 1962, the first American space project failed due to adopt replace the comma in a guidance fortune programs. And more lists, more details also given in the Wikipedia, and there is a list of software bugs with significant consequences. So in 1969, the software crisis as a term, it has been proposed by many computer scientists. It is used to describe the dilemma faced by the software development community. And in a sense, the software crisis refers to the difficulty of writing correct, understandable, and reliable programs, and also describes the difficulty of deliver a software in time within the budget. Since then, a variety of new software engineering techniques and methods were developed, such as the well-known structured programming and the object-oriented development, and some other agile development methods, and also the theories and methods to organize and manage the development activities has been proposed. But, as mentioned before, the software crisis continues to be challenging to our society. So what's the reason? Let us take a closer study at the software development process. When we develop a software, it's to produce code from the documents, like the requirement document or design document to produce the code. And in general, the requirements and design documents are written in a natural language. It is often hard to check, analyze, and reason rigorously. But the code is symbolic and formal. It has strict format and semantic. The cost to analyze and reason the code is very high due to it contains lots of language details and impression details. Let me show an example for that. For example, there is an advertisement for a restaurant. It says, if one consumes more than $100, then a 50 coupon will be given. So a guy sees the advertisement and goes to the restaurant. At that restaurant, he spends $1,620. When he checks out, he thinks the 300 coupon will be given. But the seller argues that. The seller says only 50 coupons will be given. So for the same advertisement or from the same document, different people got different understanding. So the problem, how this problem arise? Because the advertisement is written in natural language. It is ambiguous and looks confused. If we write it in a formal way, just like the following. In this formal way says, if the consumption is bigger than 100, then the coupon of consumption divided by 100 and times 50 coupons will be given. So in this way, the meaning is clear and definite. So this is just what the customer thinks. Also, we can rewrite it as the second way. It is a more formal way. That is, if consumption is bigger than $100, then the 50 coupon will be given. So this is just what the seller thinks. So here, the advertisement described in a natural language is just the seller wants to play a trick on this advertisement. So its true intention is, no matter how much you have consumed, the coupon is still 50. But from the following informal way, formal way or in formal language, the meaning is very clear and definite, and the ambiguous meaning is impossible. So from that example, we can see there is a big span between the code and between the requirements. The big span makes it hard to judge if the code meets the requirements. And this is a hard and expensive process to reason that, to judge that. Therefore, recently, the trustworthy software has been proposed and advocated by many countries and many academic communities. A software is called trustworthy if it does what people expect it to do and not something else. So as a trustworthy software, it has many attributes such as correctness, reliability, fault tolerance, security, safety, and so on. Among them, the two important attributes are correctness and reliability. Correctness is asserted when the algorithm is correct with respect to a specification, and reliability is the probability that no failures occur within a given time in a specified environment. So how can we construct a trustworthy software, or how can we improve the correctness and the reliability of a software? Many well-known computer scientists have made great contributions in this research area, and they have shown us that the software formal method and the software automation are two important ways to construct the trustworthy software, and they can help us to improve the reliability, correctness, and productivity of the software development. So the software automation is to produce software automatically from some higher level description, such as the requirements and design documents. A formal method is a mathematics-based technique for the specification, development, and verification of software. And it is a prerequisite for software automation. Also, the Turing Award winner, the well-known computer scientist James Green, has pointed out in his talk that automatic programming is the one of 12 important research goals in this century. So as a software, it has two components, programs and documents. Then correspondingly, as a trustworthy software, it has two components, trustworthy programs and trustworthy documents. Then we try to construct the trustworthy software by the software automation way, or automatic to generate the software. Then we should do two things. That is to generate programs automatically, and to generate the documents automatically. So in this talk, we focus on program generation. And in this area, there have many work have been developed in this area. And the different methods and techniques have been proposed, such as the method based on deductive inference, and program transformation, and method based on inductive inference, and using machine learning the evolution way, a model-driven development approach, and generative programming. Some notable works have been mentioned and listed here. For the method based on deductive inference, there are many works have been developed, such as the three ones, the tabular, Nerva, and the Coq. are three proof systems. They consider the problem specification as a theorem, and they consider the program development process as a theorem proof process. So they try to prove that theorem, and when the process terminates, the programs can be extracted from that proof process. So in the program transformation techniques, there are also some well-known systems like the spec-wheel, design-wheel, and prayer-wheel systems. They are developed by the Castro Institute of America, and the spec-wheel focus on the specification development, and the design-wheel focuses on the algorithm design and something like that. And in their research, they provide a library for specification or for algorithm design strategies, but they have there is no guidance on how to select a specification from that library, or how to select algorithm design method from that library. So due to the time it's tight, I can't explain it all. So go ahead. And through our survey, we found that most of current researchers adopt a top-down and stepwise way to develop algorithm. Through this way, the laws or essential laws behind the algorithm design can't be revealed, and so this way doesn't build a good bridge for that big span between specification and algorithm. It is hard to generate a subtle or ingenious algorithm, because for this class of algorithm, the logic behind them is very complex, and for the most research, there are no available effective guidance as well as procedure on how to select the proper algorithm design method. So the level of algorithm automation is not desirable, because the user don't know how to select a specific algorithm design method from the library or from the current lots of algorithm design methods. And until now, in the research, only a single or several known algorithms has been reproduced, not to mention a new algorithm. So the formalization and automation of algorithms still remains to be one of the most challenging problems in this area, and their use within the software development community has not been commensurate with its potential. And through our survey, through our study, we found the following points will be great helpful for automatic programming, like to use a unified algorithm development approach, and thus to avoid the difficulty of selection and specific algorithm design method, because it is a unified algorithm approach. And then to explore the essential laws behind algorithm design, to look inside, to look into the algorithm design process, and to obtain as many as laws as possible, and to guide the algorithm design process. So minimize the algorithm designer's efforts and make it as much as mechanical. To construct an algorithm development tool that will be very helpful. And also, a single method cannot work. We should combine new theories, methods, and techniques. And in our study, we just do like that. We propose a unified algorithm approach and develop its supported platform. And we explore the essential laws behind the algorithm design and construct the algorithm development tool. And also, we combine materials and study specific domain problems. So next, I will introduce our approach. As we know, now there are many algorithm design strategies, such as the graded algorithm, dynamic programming, and divide and conquer algorithm, brute force enumeration, and so on. But through our study on a range of case studies, we found two important strategies, that is partition strategy and iteration strategy. And we combine these two important strategies to form a unified approach, that is PAR. So we propose a unified practical formal approach for software development that contains two important steps, that is partition and iteration. So our work are supported by 12 National Science Foundation projects successfully. In the PAR approach, it consists of algorithm design language, reader language, and abstract programming language, APLA, systematic algorithm design method, and a set of program transformation system that's called PAR platform. So for a given program, we can use the reader language to describe its specification and its algorithm. We can use APLA language to describe its abstract program. And using our systematic algorithm design method, we can go through this process to produce abstract programming from the specification. And supported by our PAR platform, we can produce multiple executable language programs from the abstract program, such as C++, C#, or Java, maybe .NET. And the process is full automatic. So here we give an example to illustrate how the PAR approach can be used to design an efficient algorithm for a given problem. So the problem is there is an integer sequence A with n elements. So the problem is to design an algorithm for it to fit out the length of its longest continuous increasing subsequence. So what's the concept? Let me let's see this example. There is a sequence A with 11 elements. So it has many continuous increasing subsequence. Like let me see this subsequence. It contains two elements, negative 1 and 2. It is ejected from this segment. And so for this subsequence, it is continuous in the original sequence. And the element is increasing order, is in an increasing order, because the 2 is bigger than the negative 1. So this is the concept of continuous increasing subsequence. And there are many subsequences, but the problem is to find the longest one. So obviously, the last one is the solution. And its length, the 4, is just our solution to this substance. So for this problem, we can design its algorithm exactly. So it's easy to get this program with triple loops. It contains triple loops, and for the first loop variable I, just gives the start point of the subsequence, and the second loop variable j gives the end point of the subsequence, and the k, the third loop variable, just to visit the segment between the I and the j, and to track if the current subsequence is a continuous increasing one. So this is a deductor algorithm design, and obviously its computational complexity is NQ. So next, I will show you how to use the PAR method to develop a more efficient one, just through the step-by-step formal derivation, and at last we get a linear algorithm. So in our approach, the first step is to describe the problem using our Riddle language. So first step is to give its formal specification, and the specification consists of 3 parts. And the AQ is the precondition. It describes the constraints on the input variable or the input data. And this logic formula should hold before the program runs. And the AR is post condition. It describes the constraints on the output variable or output data, and it should hold after the program runs. So this is based on the first order logic and describes the problem very clearly. And the length is just our solution that will store the length of the longest continuous subsequence. And then the second step is to partition the original problem into a couple of subproblems. And each of the subproblems will have the same structure with the original problem, but their size is smaller. So for this problem, we just split the original problem and partition it into one subproblem. And in this equation, the capital F is to be determined because it just describes the relation between the sub-solutions and the original solution. So once the capital F has been constructed, then the recurrence has been determined. The algorithm, then we can build the algorithm. So the next step is to construct the capital F. And here, we through the transformation, through the specific transformation, step by step, and in a formal way to induce this recurrence. So here we through some transformation rules and apply this transformation rules on this specification and formal derive this recurrence. And then we can see the capital F has been replaced by the max. So this equation gives the relation between the sub-solution and the original program solution. And during the derivation, we get another new program, and hence we repeat the transformation process again and get its recurrence. So based on this recurrence, it is easy to get the Riddle algorithm. That is an algorithm described by Riddle language. So from this algorithm, we can see it is exactly a set of mathematical formula, and it has mathematical transparency. So this property makes it easier to formal derivation, and to make some mathematical operation and manipulation. So based on this riddle algorithm, we can develop the looking model, and the first step is to generate the abstract program from that riddle algorithm. So here, the program looks like usually we can see this format. So this upper language is just a detector started command language. From this program, can you see it just contains one loop. The DO and OD is one loop. So its computational complexity is n. So through the formal derivation step by step by using the transformation rules, we get the more efficient one. And the algorithm design, the algorithm ideas is embodied by the recurrence, and it is obtained by the mechanical step-by-step transformation steps. It is very natural to review these ideas instead of the manual, the before mentioned one, this one. So and after we got this abstract program, it is automatic to generate the Java program or C++ C# program. So this is the screen snapshot of our generation system. And the left side just shows the upper program, and we can just press the button to transform it to the Java program. So we can see the key ideas are here. And the upper program is more abstract and concise, but the Java program contains lots of details. So the length of this program is longer than the abstract program. Hence, the program automatically generated from the abstract program and from the formal derivation. So this is our approach, application, and the generation system. So this is a short summary for that. In general, provided that a program can be divided into subprograms and there is a recurrent relationship among program sequences, then a reliable and efficient algorithm can be generated by parse. It supports the formalization and automation of algorithms, and it can significantly improve the productivity and reliability of complex algorithms or component and database applications. Also, we have applied this approach to some important military projects in China and has made significant benefit. And based on our approach and platform, we developed some other works. After that, we studied the relational algebra. We all know the relational algebra provides a theoretical foundation for relational database. And we add this feature into our language and into our platform. So makes it very easy to write the database statement in our language, because we can use the relational algebra to implement some function instead of the SQL statement. So the relational algebra is just a mathematical formula. It is very easy to guarantee its correctness. And also, we studied the parallel and the concurrent programming and add them to our language and platform. So using our language to do the parallel programming, then you just need to use several operators, very abstract and concise. So this is our subsequent research foundation. And based on that, we further study the formal development process rules and strategies, and describe the essential rules based on the PAR method. And further, we develop a prototype system to support the application of rules and strategies to the formal derivation. We also study the domain-specific algorithm generation, including the graph algorithm, sorting algorithm, the bio-sequence analysis algorithm. And further, we also study the service-oriented computing based on our approach and platform, and to provide the support for the service-oriented computing. So here, next we will present the two works on this area. The next one is the PAR-based algorithm formal development. We study this process and generalize some rules and strategies on how to design an algorithm using our PAR method. So using our PAR method, the first step is to describe the problem in a formal way. Then the second step is to partition the problem into a couple of subproblems. So for a given problem, how to partition the original problem? Because for a given problem, there are always many different ways to partition it, like the unbalanceable way or balanceable way. So for the example, we can partition it into one subproblem, or we can also partition the problem into two subproblems, and each of them has the same size. So which way will be helpful for us to design an efficient algorithm? And the second problem is how to transform the original program specification to get expected recurrence, and how to construct the recurrence to reveal the relation between solutions and sub-solutions. Because there are many transformation rules, and how to apply or how to select them. The third step is, after we got the recurrence, and how can we generate real algorithm based on the available information. So we further studied these three programs, and we have obtained some rules. For the first problem, we got the partition rules that give some guidance on how to partition a problem into subproblems and make the resultant algorithm more efficient. And for the second program, we got the transformation strategy that gives the guidance on selection application of transformation rules. And for the third program, we got the algorithm generation rules. So this is a brief introduction of them. So these rules and strategies makes as much creative work in the algorithm design process into the routine work, because we know the algorithm design is a creative work. So through our rules and strategies, we make as much this creative work as possible into routine work, and minimizes the designer's effort. So we further develop the prototype system to support the application of that rules and strategies. Here, I'm sorry that the explanation and transformation rules are described in Chinese. But the first block is just the formal specification, and then the subsequent steps can be done mechanically. We can do partition and get one subprogram, and the F is to be determined. And then this is specification transformation. And we can, under our strategies, we can select and apply the transformation rules to the specification. So the whole process is full automatic for this program. So you can see from the specification into the next specification. Here, the Cartesian product rules has been applied, and this is the equivalent transformation. So the whole process can be automatically done, and at last we get the recurrence. And finally, through the transformation, through the transform button, we can further get the riddle algorithm. It is the same as the example before, because this is the same program as the LCIS program. So through the system support, we can get the same algorithm mechanically. Therefore, our rules and strategies, just as I have said, that it make as much creative work as possible into routine work, and minimize the algorithm designer's effort, so greatly increase the productivity of algorithm designers. And the practice shows us that with our rules and strategies, not only a no-ingenious algorithm, but also a new one for given problem may be derived mechanically. Because through this way, we have got some new algorithm, and its efficiency is better than the current algorithm. So this is our form development prototype system. Next, I will show some specific domain works. And here is the sorting program. The sorting is one of the most extensively researched subjects and the most widely used one. But although the sorting is most used, but until now, in the paper or some textbooks, some sorting algorithm is hard to describe, and such as the quick sort. Some errors often occur in the textbook or in the papers, especially the subscript error. So in the Knuth, the computer scientist, also is the Turing Award winner in his book of Sorting and Searching. In this book, he points out that from a broader perspective, the sorting makes a benchmark case study of how to solve computer program problems in general. Hence, the sorting program is a interesting subject. And in this book, about 25 algorithms have been given on this sorting program. But through our method, we generate automatically. We generate about 30 algorithms. That is more than the number of the algorithms in this book. So I will quickly go through. So this is a sorting specification for the sorting program. And then learning from the generative programming method, we are to analyze this domain, this algorithm domain, and design some components. So we get the dependencies relationship between these domain components. It has 7 components. It is abstracted or extracted from the domain. The listen and betray don't need us to implement it again because these 2 components are predefined type components in our PAR platform. So we can use them directly. And the other 5 components, we need to implement it. So how to implement this component to guarantee the correctness and reliability? And we just based on our PAR approach. From their formal specification, we formally develop its algorithm. And then, based on our PAR platform, we can generate executable program. So this is our way to develop the component. So for the two type components, that is sorting list and heap, we develop its design its implementation. This is 2 abstract data type components. And we also develop generic algorithm components, like the DBT sort. It is a component and generic. This is its implementation described by APLA, and we got it from the formal derivation from the formal specification. So we formally derived this implementation, and we can see it models an invariant behavior in terms of variant behavior. Because in this procedure, it contains 2 function parameters. I think the parameter A or the left or right, we are familiar with them. But the split and merge, we may not familiar with them because they are function parameters. So these function parameters can be used in this body, and the whole procedure is a generic one. So this generic function parameters is the variant behavior. So this procedure models an invariant behavior here, and in terms of these function parameters, in terms of these variant behaviors. So it is implemented as the 2 parameters. Also, another algorithm component is UBP sort, and also it contains 1 parameter, 1 function parameter, and it is also the variant behavior. And another is actual sort, and we formally derive its implementation from the same sorting specification. So through these 5 components, we can, through the composition of these components, we can generate specific algorithms, just like the assembly of the factory's product line. So we need to assemble this component to produce a series of specific algorithms. So through the type component, this is the type component. This is our 3 domain-specific algorithm components. And then we can assemble them or compose them, just like you build a house and to compose the brick. So we can produce a series of algorithms. And also, we can compose them in another way and produce series of other algorithms. So through the 5 components, we can produce almost 30 algorithms for the sorting problem. Also, we enhance our system to support them. This is our Upper to Java programming system, and in our system, it contains two components. One is translator, another is component library. So first, we put the sorting domain component implementation and transform it into Java component. So by this way, we get our sorting library, and then we can extend the original library with the sorting library. So this is the first step to provide system support. And the second step is to transform the composition statement into the domain-specific algorithm. So this is a snapshot for that. This is a composition statement just to compose or to assembly two components. So one is H source and another one is the sorting list. And through the statement to compose two components, we can generate its algorithm automatically. So this is the generation of some sorting algorithm and show the family of algorithms. So for this work, the correctness and reliability can be guaranteed because our components are formally derived from the specification, and after we get the algorithm, we generate the program, the C++ or Java program, based on our platform. So, and the safety, because when we do the component assembly, there are some constraints on that. And the constraints are also derived from the formal process. And it is productivity, because from the generative model we built, the serials of the specified sorting programs, including nameless ones, including some new ones, can be generated easily in multiple languages. And it is full automatic by means of the PAR platform. So through just 5 components, we can generate about 30 algorithms. This practice shows that the model has the capacity of being able to produce new algorithms. And last is our ongoing work. Recently, we want to estimate the software reliability using the first passage time. And as mentioned before, the software reliability is the probability of failure-free software operation for a specified period of time in a specified environment. And there are many models have been proposed for the software reliability. And recently, we plan to introduce the first passage time into the estimation of software reliability, because the first passage time is the first time when a stochastic process crosses some threshold boundary. And through the application, we can improve the current estimation and to get a more efficient and accurate result. Further, we can improve the software design and further improve its reliability through this estimation by using the FPT. So this is my presentation. Thank you for your attention.
Other questions? I have one. This is set up, as I understand it, to address programming problems that are best solved by partition and recurrence. Is there a good way to tell, looking at a specification, whether this approach is going to do anything good on it?
You mean the specification?
Yeah, so the thing you start with the specification, and You take the specification, you
Yeah.
dump it into this machine, it brings out an algorithm, if I understand right.
Yeah.
So how can you tell by looking at the specification whether this is the machine you want to dump it into, or whether perhaps it would be better approached by a Monte Carlo algorithm or something else wildly different from what this program is trying to do with it?
You mean how to guarantee the programs do what the specification specifies?
No, how to know whether the PAR methodology is
Yeah.
going to be effective on it.
就是说，它那个 specification 的时候，你怎么定义是用计算机来完成，还是用人工来完成？
Actually, here. In the dependency relationship here, in this, because in this approach we use it to design algorithm, and we start point in the formal specification. So the subsequent research we have done is to generate the formal specification from the program. Yeah, this specification is described. It's described using real language, but the program is not. It is in a natural language. So we have developed this one, and we define the. We have developed a system to support this step, to support the generation of specification from the program. But the program is not written in a natural language, but in a structured language. It is a structured natural language that is defined by us. So, but I think although it is not natural language, but I think the problem has been solved a little. So,
but if I start with the problem of given a natural number n, determine whether it's prime. If I dump it into this methodology, it's probably not going to come out with anything, it's probably not going to come out with a very efficient algorithm, because the ways to solve that problem are not the ways that this is looking for. How can I tell when I have a problem where this will give me an efficient algorithm, and when I have a problem where this will not?
I mean, which problem can be solved by this approach?
Yes. How can I tell, looking at the problem, whether it will be solved by this approach or not?
So here, you see, if you for a given problem, it can be partitioned into sub-problems. And there is a because relationship between this problem sequence between the problems and the sub-problems, then we can solve it using our approach.
You still need to use the formal method to analyze which one is better than the other one. You can generate a whole bunch of algorithms, but some may be good, some may be not. You still need a human being to identify which one is more efficient than the other one.
Right, but if I give the primes problem to this, it'll probably make the Civ Veritas. If I give the primes problem to some other methodology for generating algorithms, maybe it'd give me Miller-Rabin.
It's hard to tell because they automatically generate for you, and then just a whole bunch of like a 30 sorting algorithm. They probably generate 30 for you, and so you have a lot of choice from there, just like a menu. Then you choose the one what is the best for you. You still need a human being beside it from that.
Yeah, and for the algorithm complexity, you said O and square, something like that. For example, if a square is square, how many longer the program should be? How about 4 times, like 10 times? How long the program will be longer than the original one?
I think it depends the the complexity of the problem. If the problem is more complex, then the essential logic behind the algorithm, I think, is more complex. Then the Java program will be longer, maybe 10 times or 20 times than the other abstract program, because I think it's hard to give an exact measure on that. You mean here?
Mm-hmm.
Because in our language, it's very abstract, and so in different example, it has different results. Yeah, such as the Baichu transversal algorithm. The Baichu transversal algorithm, like the pre-order or the post-order, the in-order, there are 3 transversal algorithms. And in that algorithm, our abstract program is very simple, very short, just 2 lines. But the corresponding Java program can run about 50 times.
So do I need to debug the program after automatically generate?
You need to debug this.
How will that machine produce one? You don't need to debug it. It's just
You mean this system?
Yes.
Because this program is generated from this one by the system. So the system, so your problem is how to guarantee the correctness of this system. So we have in our National Science Foundation, we have a cooperation foundation with the United Kingdom. So we have built the category theological foundation, and for our system, yeah, we use the category theory to build the semantic for our system and try to improve or to convince others that our system is more reliable as much as possible. Yeah. But we don't dare to say that our system is 100% reliable. Yeah. So we only what can we do is to build a good theoretical foundation for that, and to reason, to analyze it from theoretical way.
I, for one, really want to hear more about this, but given the time, we probably should end now. There are refreshments upstairs in the usual place, and we hope many of you will join us.